Hi, good morning, everybody. My name's Clay. I work for a company called New Relic in San Francisco, and New Relic is a software analytics company. A lot of people know us for backend performance, but we also do iOS and Android. And the past few months, I've been going kind of deep on network issues affecting mobile and browser applications, but it has a much earlier origin story. Previously, I was working on an iOS app that was reasonably well received in North America, but we kept getting one-star reviews from people in France. And contrary to popular belief, there was no conspiracy theory against French users. It was really that there were some very fundamental issues with network latency on a particular cellular network inside of France. And originally it was kind of an open-ended question of like, well, how do we deal with that, and how do we design for networks that aren't necessarily 100% reliable, especially those that are far away from where we're hosting our services. And that ultimately led me down this very long path to trying to figure out, well, from an application developer perspective or from an iOS perspective, what are kind of the different tools and techniques to build more reliable applications, particularly with an eye towards the network layer. To share just a couple just technical notes on this talk, this is not a code talk. This is very much focused on the network layer. So we're going to take a fairly deep dive into the TCP and HTTP protocols, how they work, and what some of the more modern optimizations are available for developers. It's also not about the absence of a network connection either. That's a very interesting topic, but this is particularly when you do have a connection established. iOS-specific technical notes, the APIs, the classes I'll be referencing are very specific to iOS 9. iOS does a fairly good job of introducing new networking features, and several of the ones that we'll be discussing are new in iOS 9. And similarly, this, unless otherwise specified, I'm speaking of the NSURLSession class and not the deprecated NSURL connection. If you're using AF networking, that's AF networking 2.0 plus. And on that note, I want to start off talking about just the mental model that we have. It's very old of how we build networked applications. This applies to many different things, including modern iOS applications. But the basic idea is that you have an application, and it talks to some server backend that exists somewhere in the world. And increasingly, and most commonly, the protocol that connection uses is HTTP. HTTP, of course, was designed for the web back in the early 90s by Tim Berners-Lee, but it's found a very successful life in native applications as well. What's happened, though, in the past few years is instead of a single HTTP connection to maybe some API endpoints, we see more and more different connections within applications to different types of services. And these services might be controlled by you, in some backend, perhaps hosted in the cloud or otherwise. But particularly with things like Facebook authentication, Google, signing in with Twitter, we're actually making HTTP requests to many, many different services. And these are growing with different APIs and different kind of solutions you use. So it's not just, say, sign in with Google or sign in with Twitter, but different messaging APIs. Content is increasingly dynamic in applications, whether it's images, text, or data pulled from an API. And then we have this whole idea of analytics and kind of understanding how people are using the app and what the performance is, which is a separate concern. And then depending on the model of your app, we also have a lot of things around advertising as well. And the fundamental kind of theoretical underpinning of all this is the speed limit for all of these connections is the speed of light. Information can't travel faster than the speed of light. And while that, fortunately, is very, very fast, for a lot of applications, that has some very real implications in terms of latency. And to understand why that is, we have to go a little bit deep into how the transmission control protocol, the TCP protocol, actually works. And this is basically the underpinning of the modern internet, along with the IP protocol, a very storied protocol. And there's a very standard way to actually open a new connection. It's the three-way handshake, which you may have heard before. But this design decision that was made decades ago has some very real performance implications that we can even perceive. to kind of briefly describe what this is all about, the handshake, there's a SYN ACK, then an ACK, and then data gets transferred. So we have this concept of round trips, how long it takes from a bit to travel from the device, the server, and back to the device. And then we have the third step, it goes back, and then data can finally be received. So in this case, to establish a new TCP connection, the first time you're connecting to a remote service, especially with an HTTP connection, which uses TCP, you're looking at multiple round trips, which might not seem like that big of a deal, but for global networks and requests that span continents, from here to my home in San Francisco, it's just over 9,100 kilometers. It's even much further to Singapore. And even at the speed of light, and which, of course, it does not travel at the speed of light, it travels in some combination of fiber optic cables, which actually do a very good job of getting within a fraction of that. But we are very much faced with this idea of latency. So that connection, that handshake, takes hundreds of milliseconds over long distances. And so the purpose of this talk is very much focused on that. And it's, given what we know about the TCP protocol, and given that we know we're making increased HTTP connections to different services all over the internet that might be physically close to people, might be a continent away, how do we reduce that? And that's kind of the core of some of the optimizations we'll look at. The first one, and this is somewhat obscure, this was announced at WWDC last year. It's called TCP Fast Open. And the idea is, we see the TCP handshake again. Fast Open is just an interesting variation on this. On the second step, it sends a cookie. And the really neat thing that cookie allows the device to do, assuming the server supports TCP Fast Open, TFO in the first place, is the second time that connection is reestablished, because the device or client has that cookie, you're actually able to reduce the number of steps in the handshake. In this case, reducing an entire round trip. So that idea of latency, that idea of information kind of crossing national boundaries that takes hundreds of milliseconds, especially over slower, unreliable networks, it results in a fairly significant time savings. Unfortunately, and this is the kind of the downside of TCP Fast Open, but it's a good foundation for the rest of the optimizations we'll be talking about. It requires fairly new technology, and you can only use it for data that's not going to change. So an HTTP GET request, for example. Apple has more information, and I was really excited about, well, how can we actually use TCP Fast Open? This is great. We've got this new optimization in iOS 9 that allows us to kind of shave off latency. But unfortunately, and this is the downside, is that it's buried in this very, very low-level C socket API called ConnectX. So when we're talking about using it with high-level Apple networking APIs like NSURLSession, you're pretty much out of luck. To make things even worse, which this is a great kind of hackathon inspiration for Wednesday, but there's basically no code on GitHub that actually describes how to open a new socket with TCP Fast Open other than the single slide at WWDC last year. So kind of getting to it remains extremely difficult and buried deep down in system network internals. But that said, the idea that TCP Fast Open introduces that, we know that per all of these protocols, there's this certain path we take, and that path for the modern internet and for modern apps results in very perceivable network latency. And so for different protocols and different parts of networked applications, people are attacking the same problem and coming up with different solutions to shave off more round trips. A really big one, and one that's extremely important for iOS developers, is TLS, Transport Layer Security, previously known as SSL. And that's especially important because of recent changes in app transport security. So Apple's new requirement that, if you're going to make a network request from your app, it has to be secure. And it's not only just it has to be secure, it has to use TLS 1.2. There's a certain set of certificates that you're required to use. And in El Capitan, they've added this really nice command line option, -s ATS diagnostics, that allows you to check arbitrary endpoints to see if it supports ATS. But the kind of the performance penalty imposed by TLS and requiring network connections to use it, it is somewhat interesting. So again, returning to the full TCP handshake, when you add TLS into the picture, and this is the setup to create a new secure connection between a client and a server, it imposes an additional round trip. And you can actually, there's a really interesting demo on openmirage.org that allows you actually to follow along with what's happening. But it's this fairly complex specification that allows for key exchanges to create this secure connection. But creating that does come at this cost. It comes at a cost in network latency. So if we look at how to actually tune that, how to actually take that and make that more performant, we come up with kind of an interesting set of best practices. And there's a really excellent website called istlsfastyet.com. The spoiler is they say it is. And they talk about some really interesting things, but again, we're returning into this idea. We want to reduce the round trips in resuming a previously opened TLS session. And there are features in the protocol called fast start and session resumption. Session resumption, much like TCP fast open with a cookie, allows you to basically take some shortcuts if you're reopening that connection. And we also kind of see some benefits if you're using a CDN, if that's possible for your application, that to make that negotiation, that two round trip step faster by moving the servers that perform that as close as physically possible to users. And there's a lot of really interesting research in this area. The next major version of TLS 1.3, is under active research and development. And again, you see these internet researchers returning to the same idea again and again. How can we reduce the steps to establish these connections? And that brings me to a slightly higher level protocol, and that's, of course, HTTP2. Much like TCP fast open, introduced in iOS 9 as well. And a relatively new protocol. It comes directly from Speedy, which was developed by Google researchers a few years ago. And it was only ratified or standardized about a year ago in May. And again, we're getting to the same idea of kind of optimizations, better abstractions between the client and the server, and how to make that more efficient and faster. I went to the candy store a few months ago and came up with this. But ultimately, HTTP2 versus HTTP 1.1, we're using the same underlying connection, TCP, but we're able to multiplex or use multiple requests over that single connection in a much more efficient way. So we have this licorice candy versus this Sour Patch Kids rope. But with TCP multiplexing, and this is one of the core benefits of the protocol, after you've opened the connection, you can send multiple requests and receive multiple requests in their multiplex. So previously in HTTP 1.1, you can only do that one at a time over a connection. And we get to this idea of, we want to reduce the total number of TCP connections, but allow that same connection to be used in a smarter way with multiple HTTP requests and responses. It builds on some other really nice features as well. Specifically, HTTP headers have gotten quite large. Cookie data, different settings, different options. That can now be compressed in HTTP2 using an algorithm called HPAC, also standardized. And there's a really interesting new emerging part of the spec that's still not very well understood, and that's server push. If you're a Minority Report fan, it's kind of like HTTP response precog. The idea is, if the server is smart enough and knows enough about the client that's requesting, the time when it sees that initial request, it actually starts sending other data that it's reasonably certain the client will need as well. So very much designed for browsers, but has some interesting implications for native app development as well, particularly when you know or you think there's a reasonable likelihood that additional requests will be needed, and you want to just start sending those immediately without waiting for the client to request them. Not supported in iOS yet. There's considerable complexity to kind of implementing HTTP2 or building the client. It's a far more complex standard than its predecessor, and that's still very much being explored, and it's still very early. The last thing that's kind of interesting is we have this idea of different streams in HTTP2. So a stream is a channel for different sorts of requests, And those streams can be assigned different priorities, and you can ultimately build something like a dependency tree. So a client can ultimately inform a browser that it expects certain requests to be fulfilled before other requests. And again, one of these kind of new, very powerful features built into the standard, but not super well understood yet, especially for native development or even for web development from an application developer's perspective. Similarly, when we think about HTTP2 backends, it's a very mixed bag. There's a nice URL here that allows you to kind of check whether your backend supports it. It will, of course, need to have TLS. That's mostly required. It's not required by the standard, but it's required by basically every vendor. And there's also a way you can do it on the command line with the OpenSSL client. But the idea is that this, while it's improving fairly quickly, you're going to need basically a very current operating system and new server software as well. Just last month, Nginx, the popular web server, pushed HTTP2 support to their mainline branch. So it is slowly catching up. And when we talk about kind of actually implementing HTTP2 or using it in applications, it's built in to NSURLSession, so you get it automatically if the backend supports it. But the caution is that, imagine if your backend does support H2 and yeah, you're using iOS 9, new APIs, it kind of just starts using it. The implications of doing that are still very much being discovered and explored. So there's kind of you have to kind of proceed with caution, more or less. And part of that is most of the server-side TCP stacks aren't especially tuned for HTTP2, and best practices are still being developed. So when we think about all of these flips we can switch on the server that optimize how these connections are made and established, it's something that's still very much being explored. Similarly, and kind of the shortcut to implementing this is many content delivery networks support HTTP2 out of the box. So if you're using a content delivery network in front of your servers or your APIs, it's very likely that the connection between the CDN itself and the device is in HTTP2. In general, and this comes with any sort of major networking change, having measurements in place before and after is really critical, especially as people are trying to figure out, well, what are the best practices for doing this, and what does this actually mean when I turn this on? One bit of really encouraging news is at Facebook's F8 developer conference a few weeks ago, Instagram announced they turned on HTTP2 for the Instagram app. It doesn't get much bigger in terms of scale than that. And they were able to measure a 23% reduction in latency and a 1.1% increase in overall impressions. So some pretty impressive numbers, but being able to kind of defend the choice with numbers is really important to have some measurements in place. We've gone fairly deep into kind of network protocol land and how that applies to iOS apps. To shift a little bit to caching, obviously, in terms of performance, making all these network requests is very expensive. It's even better if you can reasonably determine that you don't even need to make one in the first place. And this is provided very clearly by standards that have existed for a long time. And for NSURLSession, it automatically, by the default option, which makes it somewhat clear, NSURL request use protocol cache policy, which basically says, by default, it will observe the directive supplied in the cache control header when it gets an HTTP request back from the server. And the cache control header has many different options. It's quite complex. You can mark to never cache, to cache for a specific amount of seconds, public or private. But at its core is just the idea that servers can inform clients how long to keep a local cache of the asset that was requested. And max age is particularly interesting and useful that if you know, for instance, a static image or any static content is unlikely to change, you can set a very long-lived max age, and so additional network requests won't hit the server anymore. As with anything, this is very much application-specific, and you have to kind of determine, as a developer, what the correct caching policy is for your application, which, of course, gets pretty challenging pretty fast. The second variation also built into NSURLSession is just the ETag header. And unlike cache control, where you're actually maybe caching an asset locally in memory or on disk, ETags, it actually still makes the request to the server. But it's especially interesting for dynamic content. So here, let's say we have a JSON document that lists a list of favorites. Much like before, you using NSURLSession or AF networking, you make the GET request, it returns that, but it also includes an ETag, and the ETag is an MD5 hash of the contents of the file. And so the client remembers that, and then when it makes that same GET request again, it passes along the ETag, if none matched, and if that content on the server matches the representation on the client side, instead of getting back the 200 and the entire response body, you just give it back a 304 not modified. And that's important certainly for bandwidth, but particularly for very large JSON documents or requests and responses that maybe take a long time to parse, knowing that it's not modified and you already have the correct representation locally can be a pretty large savings as well. We've gone over a lot of kind of networking stuff, caching, HTTP2, different TCP and TLS optimizations. But the really important thing, particularly as a developer, is, well, all of this stuff is really great. There are dozens of these different knobs I can turn and different things I can optimize. But how do I understand what's actually going on over the wire? And there are several different ways built into iOS that can do this. Mostly in order of kind of most fine-grained to kind of least fine-grained. The first is an environment variable cfnetwork_diagnostics. You set it in the scheme editor for its value from 0 to 3, where 3 is the most detailed. And it creates this local log. And the log is quite complex. This is with the level of detail turned all the way up for 3. And you actually see, like byte by byte, everything that's going on over the wire. This screen capture, and I know it's hard to see, this is actually part of the TLS negotiation. You can see here on the right-hand side, it says H2-16 speedy HTTP 1.1. This is the step of the protocol of TLS that's actually determining what type of application protocol the client can talk to the server. It's called ALPN. So this is actually the step that allows the iOS device and the server to establish that they both speak HTTP2. And you see that kind of buried in the text there towards the end. But extremely fine-grained, a lot of very sensitive information as well, but certainly very powerful to kind of understand byte by byte everything that's happening for an app over the network. Similarly, and also available in iOS, is the remote virtual interface. And this is for a physical device that's plugged into your laptop using USB. And after you've plugged in your device over USB, you open up RVI control and you give it the device UDID. And that'll actually create a new interface on your laptop that you can then use a packet sniffing tool to then see the network traffic over. So one of the most popular tools with the UI, you might have heard of TCP dump. This is very similar, same category of tools. But with Wireshark, you launch it, it looks like this, and you select an interface. With Remote Virtual Interface, you'll see a new option, RVI 0. And when you select it, you'll start seeing all of the TCP data, all of the network traffic that starts going over the wire. Here you can see the TCP packets and also TLS as well. And because most of the traffic is encrypted, unless you have the certificate, you're just going to see the TLS exchange and the TCP packets because you don't actually know what's inside of that TCP packet because it's encrypted. And we'll get to how to get around that shortly. There's an instrument for everything, and of course, there is a network instrument. This, of course, requires you to have the source code to run instruments. And I'm not a huge fan of this particular tool. It allows you to see the connections and kind of a higher level view of the number of bytes and kind of also a very similar TCP view that organizes them, but hasn't really been my first place to go. And if anyone really loves network instruments, would really like to hear how you're using it and then what problems it's solving. For application developers, using Wireshark or network instruments is kind of a nice starting point, but something that's slightly higher level and allows you just to view the HTTP requests is obviously very useful. There are different tools that do this using a proxy. The idea is between your device and the services it's accessing, you put a proxy server up in between, and then you're going to use that proxy server to get information about what's actually going over that. In this case, an HTTP proxy to actually see what's going on in that application protocol. There are different sorts of HTTP proxies out there. Because HTTP2 is so new, there aren't many that support it out of the box. One of the very few that does support it, as of only a month and a half ago, is mitmproxy, which as of version 0.16 does support it. And it does have an interface. It's not completely buried in the command line, but it is something you do run in a terminal. Here's a screenshot of it right there. And it's surprisingly difficult to install in El Capitan because the Python instance, the Python version has some issues. I would suggest using Brew. But once you're actually running it, you basically configure the OS 10 proxy to point to man-in-the-middle proxy, which just by default runs on the server on port 8080. And because you're ultimately, and because of ATS, you're very interested in what's actually going on with that encrypted network traffic, that HTTPS secure traffic. They've got a really nice way to kind of install the certificate. If you're running on the simulator or if you're running it on your device, you navigate to a special domain name, mitm.it. You'll see a nice Apple logo. You tap it, and it'll install the certificate. And the really cool thing that happens next is you'll actually start to see all of the HTTP requests and their responses in the command line as they happen. Here's an example that's just a screenshot of the proxy itself. So in this case, I have my iOS 9 application, and I'm making a request to ng-http2.org, which I know is a site, a domain that's using HTTP2. And because this proxy server does understand HTTP2, it marks it on the top there as an HTTP2 request. And you're able to see all of the headers and the request headers, the response headers, and the response body as well. It's an extremely powerful tool, and it's especially interesting for kind of deconstructing how different apps are actually using the network and what their API endpoints and story is. It's fairly advanced. You can actually pause the requests and edit them in real time. One of their demos, it's kind of funny. It's how to use this tool to increase your high scores on Game Center. So it has a lot of power. But I think a really great starting point to kind of understanding the HTTP traffic that powers the application, what its characteristics are, and whether, of course, it's using HTTP2 or not, with some other very, very advanced tools. One nice thing is in NSURLSession, the nice thing is it gives you the version of the library. So NSURLSession uses Core Framework Network, and it has the version. So you're able to kind of use that user agent information to understand what exactly is kind of issuing that request, unless you override it. We know a lot about kind of, well, we have this connection between the client and the server, and there are different ways we can optimize it, we can debug it, but there's also just kind of this manual testing idea of, well, we want to make sure that on bad or slow networks, on lossy networks, our apps behave in a reasonable way. Facebook has an excellent open source tool that actually is essentially a gateway controlled via software called augmented traffic control that allows you to control this in a very complex way, an advanced way. Apple also has the network link conditioner, which I'm sure many people have heard of and used. It allows you to simulate slow networks. NSHipster, of course, has a really excellent guide on more about that. But I think it's kind of about time that we think of like, well, what's the high performance network checklist? And I think we can see a lot of best practices in how these protocols are actually designed and what the direction is, particularly with HTTP2 and with TLS 1.3, these things that are actually being delivered by standard bodies and then implemented by vendors like Apple. We know the network is unreliable, and there's certainly a cost to establish a new TCP connection and have multiple round trips. We really want to reduce that. Second, and this is, I think, important too, that kind of rolling your own caching scheme in many, many cases is very unnecessary. There are very well-defined standard ways to do this in the HTTP protocol itself that's automatically understood and implemented by NSURLSession, among others. And kind of leveraging that ultimately just saves time. And lastly, and I think this is especially important, that the network really shouldn't just be this black box we don't care about. And as our applications become more networked and more connected to different services around the world, having the ability to have an understanding of what's actually going on, what happens over the wire, and what the performance characteristics of it are, is I think very important, especially as our apps basically become more distributed. And finally, just kind of a last thought here, and that's that ultimately it's very interesting, or at least I do, to kind of dive deep into networking and kind of ponder, well, what does this mean for how we design apps, how we make network calls, what are the best practices, and kind of what do these protocols enable us to do to make faster apps? But unless you're building an app for a network engineer, the person who uses the app probably could really care less about what protocol version you're using or what TLS certificates you use. But they do obviously care very deeply about the app being fast. And so I think when we kind of consider all these options, or whether to take a very deep look at whether we should implement HTTP2 or kind of have a more advanced fine-grained caching strategy, the goal, of course, should always be just to make the app faster and more responsive. And I think that's really just the most important thing. On that note, the slides, I think, will be posted on Slack and Twitter very shortly. But on that note, yeah, thank you very much.
So we have time for 1 or 2 questions. Are the volunteers here with the mics? Yes, we have 2 volunteers here with the mics. So does anyone have a question? By the way, I want to excuse myself. I think I mispronounced your name. I'm very sorry about that. So, everyone very shy. No questions. There is a question over there.
Hey, if there was one thing that we could do to think about for improving the performance of our apps networking, what would it be?
It would absolutely be to reduce the number of HTTP requests. Regardless of kind of what version of the protocol you're using, it's just bundle absolutely your requests where possible. And I think a very simple thing to do as well is to look at or consider using a CDN.
Cool, thank you.
Another question? Any more questions? Don't be shy. We're all friends here. Yeah, here we go. Over there.
What would I actually have to do if I wanted to support HTTP2? Is it just a matter of exchanging my Apache in front of my application server with a new version, or?
Yeah, that's a great question. So if you're implementing HTTPS, there's a really great new and free open source project called Let's Encrypt, let'sencrypt.org. And they have some really nice clients that step you through the process of enabling TLS on your server.
No, the question was, if I wanted to implement HTTP2 support, how would I do it? Is it just exchanging my Apache in front of my application server with a newer version, or?
Yeah. Yes, the latest version of Apache and Nginx do support HTTP2, and obviously TLS is required. So if you update the version of your web server software in front of your backend, you would get HTTP2 support.
Great, thank you.
Sure.
Okay. There is another question over there. Yeah, here we go.
So what about packet size versus number of requests? Let's say you have a big table view and you have a detail view. How much should you load up front and how much should you reserve for later requests?
That's an excellent question. And there's an excellent article on TCP tuning, kind of tuning the TCP server-side stack. One thing that a lot of people are looking at is the initial congestion window of TCP. And obviously, like kind of tuning the packet size and the TCP stack gets quite technical very fast. But the document on the slides goes into a lot of detail on kind of what the best practices are for that packet size and how to optimize for different sorts of networks. But I think something absolutely worth looking into. But there's definitely an art to TCP tuning, and I'm happy to follow up with you with that link there. I think it's a really great place to start.
Okay. Thank you.
Thank you very much.
Thank you.